Okay, let's get ready to rumble. Logarithmic model. This is example number 2 on, or 5B on that page. So what I did is I already preloaded the data into the equation editor or this list. So in list 1 I've got all the y values, or all the x values. In list 2 I got all the y values, and now we're going to go through the same procedure we did before. We're going to try to linearize this data, and what they're telling us in advance, which is kind of nice, they're saying, look, this should be data that is modeled well by a logarithmic model. Our job then is to take this data, find the best curve of best fit using this linearization process, and bring it back to a logarithmic model that we can use to model the original data. So with that being said, the first thing we do is we try to get a good picture of this. I think it's important to kind of come back and see what you're looking at on these. So first thing, we're going to get a window that we can see this all on. So at this time it's going from 1 to 8, so a negative 2 to 10 should work. And our y values are much smaller this time, so I think a negative 1 to 12 should work fine for what we're looking at here. And we want to go by increments of 1. Enter. So if we graph, we should get a good scatter plot. If we go back, and I always got to remember I got to clean this stuff up because those are old equations. We'll have to clear them out. And if it's done right, this plot 1 should be plotting things in list 1 and list 2. I want that to be on, and graph. Okay, now this is why they think a logarithmic model is a pretty good model. It's increasing at a decreasing rate. That is something that we'd want to look at as far as some of our ideas on this. It could also be represented by a square root model. I mean, think about the nature of the family of square root models, that has a little bit of a resemblance of that. But they specifically tell us to use a logarithmic model. So because we think it's a logarithmic model, and they're telling us that, I guess, we come back up here and they say, how do you transform that data? Well, if we think it's logarithmic, which they say it is, then we transform the x values but leave the y values alone. So we have to transform the x values by taking the natural log of x. So that's where we go, and we start editing list 3. So enter, come over to list 3, and what do we want to do to it? We want to hit enter on list 3 once it's highlighted up in the top, so that the list 3 is highlighted. Now we want to take the natural log of all the list 1. So we're going to do natural log, and we're going to tell it to the natural log of everything in list 1, close it to be syntax correct, enter, and now there's all of our x values. All the x values are going from 0 to, and the highest it gets to is 2. 2.07, so I really only have to go from 0 to 3. So when we do redo this and we look at our scatter plot, we better fix our window. So if I do this and I go back to stat, I come back and I want to see plot 2. Okay, I want to turn it on. Got to be a little bit careful. We got to come down here. Our x's are now in list 3. The y values that were associated with those ordered pairs were in list 2. And we're going to graph those with those dots, and I'm going to show you again that you probably have to resize your window. See how bunched up those are? Those are our transformed data. So let's go back to our window, and let's set them up, because the y values were not varying very much. They were going basically from 0 to 3 if my memory serves me right. I didn't change the y value, so I shouldn't have to change the y min and max. And then the other thing I'm going to do is I'm going to get rid of our other scatter plot. There's no sense looking at it. Let's just go to y equals. It's just as easy to turn it off there. So go up to y or plot 1, turn it off. Let's look at plot 2. And you can see that the data looks like it has been linearized. It's got a little bit of a bow and a kink in it, but the entire path as a whole looks like it's been linearized. So that's exactly what our data should look like if we have the right transformation. Step number 2 here, and really we're just going to ask the calculator to do another feature for us. Since our data is now linear, we want it to find the line of best fit. So we're going to do a linear regression on that new set of data. Okay, so where were the x's in? They were in list 3, so you're really going to have to pay attention to where your transformed data is and where your original data is. Your original y values were in list 2, and we didn't have any frequency. We should never have that. We want to store the regression equation. Absolutely, that's a great idea to do. That means we keep all the digits of precision. In list 1, we're going to calculate, and we're going to see how good this fit is. Again, our fit is very high. If you look at your correlation coefficient for this linear, it's 0.998. That's a pretty good match with the data. And now that should be stored in your equation editor. So if you want to see how great that fits and just see how wonderful a job it's done, you can see that it goes through our crosses very well. Okay, so let's go back to our home screen. And I got to run that regression again, I guess, because I must have taken it out. That was our linear regression. Okay, so what I needed to grab off of here, which I forgot right after we ran that regression, is I got to get the slope and the y-intercept of that. So I'm going to move it down, give me some workspace. I'm going to record. This time, it's the y values that are the same. So here's what we're putting in. We're putting in the form y equals ax plus b. But the thing that we transformed on this one, not the y values, we left the y's alone, we transformed the x's. So I put a hat over the x plus b. So this is the linear equation for the transformed data when the x's got natural log. So the slope on this is 2.99, so I'm going to put in 2.99 x hat plus. Now I want to know the y-intercept, so I'm going to grab that. The y-intercept was 5.05, so plus 5.05, and that should be the equation of the line of best fit for the transformed data. Our job now is to take this and turn it back into an equation that'll fit the original data. So I got to take this equation, which is the line of best fit for our transformed data, and convert it back into an equation that will model the original well. So what did x hat stand for? What did we do to the x values to linearize the data? And that was we took the natural log of all the x values. So we got to plug that in for the y or the x hat. So 2.99. The x hat's coming out, and what we did to create that was the natural log of x plus 5.05. So how can we rewrite this as a log function? Well, we really do have a log function in here already. What we might want to do is use a power rule and say this is y equals the natural log of x to the 2.99. Maybe we could have just rounded that to 3 plus 5.05. Now this should be the model that should be the equation that models the original data well. Now the only way I can get that in there is to come back into the equation editor, and that's where we are going to type that. You can put it in 1, but I'm just going to put it in 2 here. And we're going to take the natural log of x cubed. Well, I guess I have x to the, what do we got there? 2.99, since I rounded to the hundredths. And that's the end of my exponent. So now I want to put a parenthesis to end the argument of the natural log. So we're taking the natural log of basically x cubed plus, then we got 5.05. Okay, I'm going to deselect equation number 1 because that is not the equation I want to see graphed in anymore. I want to go back and see the original data set graph, which is in plot 1. I don't want to see plot 2 anymore. And now that I went back to the original data, I have to change the window back to what the original window should be, and that just means change your x's back from a -1 to 12, I guess is what we have. And if I hit graph, it should graph the original data with a scatter plot, and here comes our curve of best fit. This curve of best fit was found by the calculator. We made the calculations this time to transform the data to linearize it, and then we ran the linear regression, and the calculator did all of its algorithm to find the least squared regression line, some of this least squared regression line, and that's your curve of best fit. So a couple of examples on how this is working. There are some unique things in everything that shows up here. Make sure that you are diligent in doing your homework. I'll try to pick things that model each kind of power model or quadratic model and so forth, so you have practice in all of them so you're not caught off guard if it shows up on one of your assessments. So best of luck to you. I will do one more example for you to follow along, and that will conclude our video series on this. So stopping it now.